Hello and welcome to the Deep Learning lecture. This is the introductory unit with the learning goals to get an understanding how deep learning relates to machine learning, to get a basic understanding of the concept of representation learning or feature learning, and to understand what are the typical use cases and data types deep learning methods are applied to.
To answer the question, what is deep learning, one can first ask how machine learning relates to artificial intelligence. Machine learning is a subfield of artificial intelligence, and it is the field that studies algorithms which can learn from and make predictions on data. Now, deep learning is a subfield of machine learning. And it's a field that uses so-called artificial neural networks for learning from data and for making these predictions. Now, deep learning itself is not new. Neural networks have been around since the 70s. And also back then, deep neural networks, that is, neural networks which have multiple layers of hidden neurons, were used already. So one can wonder why, if everything is so old already, everybody is talking about deep learning right now. And there are several reasons for that. First, nowadays we have specialized and powerful hardware that allow to train huge neural networks. Second, large amount of data is available. Third, we know special kinds of network architectures which were specifically designed for certain image types, for certain data types like images or text data. And fourth, we know better optimization and regularization strategies. We will learn about these in the course of the lecture. Yoshua Bengio, one of the fathers of deep learning, and one of the three guys that got the Turing Award 2018, defines deep learning as machine learning algorithms inspired by the brain based on learning multiple levels of representations or abstractions. Learning multiple levels of representations or abstractions, what does it mean? We could, for example, ask a machine learning algorithm what is shown on this kind of image and would like it to output that it's a bird. Now, when we make this kind of classification ourselves, we look at certain features of the image, like the beak or the feathers, to decide that it's a bird shown on the picture. A machine learning model, like a neural network, however, would not get these pre-selected bird features as input, but the raw data. That is, in that case, the pixels of the image. Representation learning or feature learning now refers to a set of techniques that allow the model to automatically discover the features or representations needed for the classification tasks. A deep neural network is a hierarchical architecture. It is inspired by the brain in that it stacks multiple layers of learnable nodes. In that case, we would have two of these layers, each consisting out of several nodes. The output of each of these layers can be seen as some representation of the input data, and the representations of a lower layer serve as input to the next layer. This allows to learn more and more abstract representations. In this illustrative example, the first layer, for example, learns to recognize local image features like edges. And the second layer learns high-level features like the beats or the feathers. This, of course, only gives a rough and high-level idea about what representation learning is, but we will get a much better understanding of that in the course of the lecture. Deep learning is extremely valuable if the data has certain properties. First, if the data is high-dimensional. Then, if each input itself is not informative, but it becomes informative if you take it in combination with the other inputs. Then, if there's a large amounts of data available. This implies that for certain types of data, deep learning is not the method of choice. For example, if we have tabular data, where we have only a few entries per data point, and each of these entries is meaningful itself. In such a case, methods like random forest or gradient boosting could outperform deep learning. But the properties that we need are matched in a lot of cases. One of these cases is with image data, because if we have images, these are certainly high-dimensional. You can see that if you, for example, consider an image of size 255 times 255 pixels. With that, and 3 color channels, since color images are encoded with 3 color values, we have already about 200,000 input features. Of course, a single pixel itself is not meaningful itself, but only in the combination with the other pixels. And depending on the applications, with images, there might be a lot of data available. So what could you learn? What kind of task could you learn to fulfill with a neural network on images? First is, of course, image classification. As in this example data set, where we have different kind of images, and the network can decide if what is shown on the image is an airplane, a deer, a dog, and so on. So, given an image, the network outputs what is seen on the image. Another possibility is object detection, as here for the example of autonomous driving or self-driving cars, where you get an input image or an input video, and you want to classify the objects shown on the image. So there are several objects per image, as for example the passenger here, a traffic light here, or the car here. So given the image, the network outputs what kind of objects are shown on the image and where they are shown. Another image-based task is image segmentation. That is, given an image, we would like to find out which segments of the image belong to the object shown. For example, here, these segments belong to the dog shown on the image. Other possible data type is text. In text, each word is a single feature. And of course, there are a lot of features. For example, the German language contains more than 3,000 words. And text is usually composed out of a lot of words. A single word itself is again not so informative, but only several words in the text are. And again, you can have a lot of data available depending on the application area. A task that can be performed on text data is, for example, sentiment analysis. That is, given some text, identify what kind of emotion is behind this text. This could be useful, for example, for automatically classifying reviews for a product, a film, or so on. Here, for example, if you have the text, "Great job, your customer support is fantastic," you would like the algorithm to find out that this is a positive meaning. As another example, if someone wrote, "The worst customer service I have ever seen," you would like the algorithm to identify that this meaning of the text is negative. On text, machine learning models, and specifically deep learning models, can also be trained to perform machine translation. This is what we usually have when using Google Translate or methods like DeepL. We provide one sentence in one language, like he loves to eat in English here, and the algorithm automatically translates it to another language. Liebt es zu essen in German. Finally, we can also apply deep learning to other kinds of data than images or text. For example, speech. Speech recognition or generation is used with your Google Assistant or Alexa or Siri. So there's a lot of advices where you can, which automatically recognize speech and can produce some. And this usually also relies on neural networks.